Module 10, Lecture B, Slices, Hash Format. By the end of this lecture, you will be able to create and use slice objects explicitly to index and slice sequences in flexible ways. Use hash to inspect hashability and understand how objects behave in sets and as dict keys. And apply format and related built-ins like ASCII and ORD to produce and inspect string representations. Working with slice objects. Building slice objects. Slice objects act like detailed instructions for selecting parts of a sequence. Instead of using bracket notation directly, you define a slice with a start position, a stop position, and a step, which can be numbers or left blank. This definition becomes a reusable guide, such as starting at the third item, going up to the 10th, and taking every second element. You can then apply this same guide to different sequences, like lists or strings, to consistently extract the same pattern of elements. When working with slice objects, you need to understand how the start, stop, and step parts behave, especially when some are omitted or negative. The start marks where the slice begins and defaults to the first element, while the stop marks where it ends and is not included in the result. If you leave out the stop, the slice continues to the end. The step controls how many elements you skip between items and defaults to 1. Negative indices count from the end of the sequence, and a negative step lets you move backwards through the data, which is useful for accessing recent or last elements. In Python, slice objects can be created dynamically based on user input, configuration data, or earlier computations. For example, you might compute start and stop positions from a quarter number when working with weekly sales data, or use chapter markers to define slice boundaries in text processing. In data analysis, you can also set a step size to sample data at regular intervals, such as every fifth sensor reading. Defining slices this way keeps the slicing rules separate from the data itself, which makes your code more modular and easier to adapt. Python code, building slice objects. This section explains how to explicitly create slice objects by specifying their start, stop, and step values rather than writing slice notation directly. It shows that a single slice object can be applied to multiple compatible sequences, allowing you to reuse the same slicing pattern. It also highlights how leading out some of these values or using negative step values changes the behavior of the slice and enables more flexible ways to extract parts of a sequence. We begin with a list of numbers that represent measurements in inches, used to show how slicing works on numerical data. Alongside this, we create a short text message made of the letters A through H, which acts as a similar example using characters instead of numbers. By setting up both a numeric list and a text string, we can demonstrate that the same slicing techniques apply to different kinds of sequences. This highlights the flexibility and reusability of slice operations across multiple data types. We define a slice object that selects elements starting at index 2 and going up to, but not including, index 7, taking every second element. In other words, it chooses every other element within that index range. This slice object can then be applied to different sequences, so you can reuse the same slicing pattern consistently without redefining it each time. We use a slice object called quarter slice on a list of measurements in inches to select elements starting at index 2 and going up to, but not including, index 7, taking every second element. This means it chooses every other value within that part of the list. We then apply the same slice object to a text message, showing that one slice definition can be reused on different kinds of sequences, such as lists and strings. Finally, we print the results to compare which elements were selected from each sequence using the same slicing logic. We create a slice object that starts at the beginning of a sequence and goes up to, but does not include, the element at index 5. The step value is left at its default of 1. This slice can be used to extract the first 5 elements from any compatible sequence, such as a list or a string. By explicitly using the special value that means no value for the start and step, we clearly indicate that we are relying on the default behavior in an intentional way. This example shows how a slice object can be used to select elements from different sequences. A single slice, called the front slice, is applied to both a list of measurements and a text message. It starts at the beginning and goes up to the 5th index, using Python's default step of 1. By leaving out the start and step values, we rely on default behavior, while still clearly expressing our intent. The result is that we print the first 5 elements from both sequences, demonstrating that the same slice object can be reused across different types of data. This slice object is set up to move through a sequence in reverse, starting from the last element. The starting index is -1, which means it begins at the end, and the stop value is left open, so it continues all the way to the beginning. The step is -2, so it moves leftward and selects every second element. This lets you easily pull out elements from the end of a sequence in reverse order while skipping one item each time. We use a reverse slice on the list of measurements to select elements starting from the end and moving backward, taking every second item. This creates a view of the list that goes from the last element toward the first, skipping one element each time. We then apply the same reverse slice to a text message, which similarly selects every second character while moving backward through the string. This shows that a single slice definition can be reused on different sequence types to produce consistent slicing behavior. This script shows how slice objects can be used to extract parts of sequences such as lists and strings. It first creates a slice that starts at index 2, goes up to, but not including, index 7, and takes every second element, then applies this same slice to both a list of measurements and a string. It then builds another slice that selects the first 5 elements, demonstrating that leaving out the start and step values makes it begin at the start and move one element at a time. Finally, it uses a slice with negative indices and a negative step to move backward through the sequences, picking every second element from the end. Overall, it highlights how slice objects let you navigate sequences flexibly in both forward and reverse directions. Applying slice objects. Once you understand how to create slice objects, the next step is to use them intentionally on sequences. They work like regular slicing, but give you more control, especially when the slicing rules are decided while the program is running. Applying a slice object tells the sequence to produce a new view based on its start, stop, and step values. For example, you can use one to pull out every third temperature reading from a list of daily values. In this way, the slice object serves as a reusable guide for navigating a sequence and extracting exactly the subset of elements you need. Slice objects are especially helpful when working with data structures whose layout is only known at runtime. For example, if each log entry is a string with fixed positions for a timestamp, user ID, and action, you can define slice objects for each part and reuse them whenever you extract those fields. This avoids hard-coding index boundaries throughout your code, so if the data format changes slightly, you only update the slice definitions in one place. As a result, your code becomes more readable, has less duplication, and is less prone to off-by-one and similar slicing errors. Slice objects work the same way across different sequence types, such as lists, strings, and tuples, because they automatically adapt to the length of the sequence. You can reuse the same slice on different data types, and it will still behave correctly, even when using negative indices or step values. For example, you might use a slice to select the last week of stock prices from a daily list, or to pick every fifth character from a long string. By viewing slices as flexible guides for moving through sequences, you can apply them consistently in many contexts, including text processing and data analysis. Python code, applying slice objects. This section focuses on how to use slice objects across different kinds of sequences and how to reuse common slice patterns. It explains how these patterns are especially useful when working with logs or measurement data, where you often need consistent ways to select ranges of entries. It also emphasizes using negative indices so that slices adapt automatically and sequence lengths change, allowing you to reliably access recent or trailing data without recalculating exact positions. We begin with a list of daily temperature readings measured in Fahrenheit, containing 12 values, one for each day. This list serves as our basic dataset. We will use it to show how slice objects can efficiently access and work with selected portions of a sequence. The focus is on demonstrating how to extract and process specific subsets of these temperature readings. We use a slice to pick every third day from the list of temperatures, starting at the beginning and continuing to the end with a step of 3. This samples the data at regular intervals instead of using every value. Doing this can reduce the amount of data we work with and help us focus on periodic patterns in the temperature readings. We use a slice object called every third day to pull specific elements from the temperatures list. This slice is set up to select every third temperature reading, starting with the first one. When we apply this slice, we create a new list of sampled temperatures that includes only those readings taken every third day. This method lets us sample data at regular intervals without having to list each position by hand. We start by printing the full list of temperatures in Fahrenheit to see all the data. Then we print a smaller set of temperatures taken every third day, created using a slice object that selects elements at regular intervals. Comparing the full list with this sampled list shows how the slice object efficiently extracts a repeating pattern from the original data. This highlights how slicing can be used to focus on specific, regularly spaced values within a larger dataset. We begin by building a log entry as a single string that contains 3 parts: a timestamp, a user identifier, and a description of the action. These parts are separated by vertical bars, which serve as delimiters. Using this consistent structure makes it easy later in the code to isolate each component. We can then extract and manipulate the timestamp, user information, or action description independently by applying slice operations to the string. We define slice objects to consistently extract parts of each log entry. The first slice takes the timestamp from the start of the string through the 19th character. The second slice captures the user identifier from the 20th to the 30th character. The final slice takes the action description from the 31st character to the end of the string. Using these fixed slices makes it easy to reuse the same logic for any log entry with the same structure. We use predefined slices of the log entry string to consistently extract its key parts. One slice selects the timestamp so we can pull out the date and time. Another slice targets the user identifier, which uniquely represents the user involved in that entry. A third slice captures the action description, such as a successful login. By applying these slices, we turn each raw log entry into structured data that is easier to analyze and process. This example shows how slice objects can be used to pull structured information from a log entry. The code first extracts and prints the timestamp from the start of the string up to a specific character position. It then extracts the user identifier from the next section of characters. Finally, it takes the remaining characters as the action description. By reusing these slice objects, the code can consistently extract the same parts from similar log entries. This example shows how using negative indices in a slice can automatically adjust to changes in a sequence's length. By setting the start index to -3, the slice selects elements starting from the third item from the end. Leaving the stop index unspecified lets the slice continue to the end of the sequence, and using a step of 1 includes every element in that range. This approach is useful because it always returns the last 3 elements, no matter how many items the sequence contains. We can use a slice to get the last 3 elements of the temperatures list by starting 3 positions from the end and going to the end. This slice pulls out the final 3 temperature readings in one step. Because it is based on positions from the end rather than fixed indexes, it automatically adjusts to the list's length. This makes it especially useful when working with data that changes size over time. We update the temperature list by adding 2 new readings, 79 and 81, to simulate more recent measurements. After this update, we reuse the same slice description that selects the last 3 items in the list. This shows that the slice automatically adjusts to the new list length. As a result, it always returns the 3 most recent temperature readings, even as new data is added. We first print the last 3 temperature readings from the original list to show how a slice can capture the final 3 elements. Then we extend the list with new temperature values and print the last 3 readings again using the same slice. This shows that the slice, defined with negative indices, automatically adjusts to the new length of the list. Overall, it demonstrates that negative index slices are flexible and always track the last part of a changing sequence. This script shows how slice objects can efficiently extract and manipulate data from sequences. It uses a list of daily temperatures to demonstrate selecting every third value, making data sampling simpler. It then applies slices to a log entry string to pull out structured parts, such as the timestamp, user ID, and action, reusing the same slice patterns for consistent extraction. Finally, it uses negative indices to grab the last 3 temperatures before and after adding new data, showing how slices automatically adapt to changing sequence lengths and are useful for handling variable datasets. Reusing slice objects. Once you understand how to create and use slice objects, their main advantage is that you can reuse them without rewriting the same details. A slice object acts like a template for selecting parts of a sequence, so you do not have to repeatedly specify the start, stop, and step positions. You define the slice once and then apply it wherever needed, especially when working with data that share a common structure, such as lists of measurements or similarly formatted strings. This reuse makes your code clearer and reduces mistakes that come from typing index ranges over and over. In larger programs, it is helpful to reuse slice objects whenever you need the same slicing logic in multiple places. For example, if each log entry starts with a fixed length timestamp, you can define one slice that selects the timestamp and apply it to all entries. If the log format changes, you only need to update that single slice, and all related code will automatically adapt. This works like using named constants to centralize important details. But here you centralize how sequences are structured, which makes the code easier to maintain and less prone to errors. Slice objects can do more than just reuse parts of a sequence. They can define abstract access patterns that work across different but similarly structured data. For example, you can define slices for a record's header, core, and checksum, and apply them to numbers, bytes, or strings that share that layout. In analytics, a slice can select every nth sample from time series data, so you can compare sensor streams at consistent intervals. Giving these slices meaningful names also serves as documentation, emphasizing stable regions in a sequence and helping you treat sequences as structured data with clear, reusable segments. Python code, reusing slice objects. This section explains how to define reusable slice objects so you can access the same parts of sequences repeatedly without rewriting the slice each time. It illustrates how a single slice can be used to extract timestamps from many log strings in a consistent way. It also shows that when you update the definition of that one slice, all related operations that use it automatically reflect the change, making your code easier to maintain and adapt. We create a list called logs that holds several strings, where each string is a log entry containing a timestamp and a description of a user action. This list simulates a sequence of log entries that we might see in a real system. By storing the entries together in a list, we can easily loop through them, analyze them, or perform operations like extracting just the timestamps from each entry. We create a reusable slice object that always selects characters from position 0 up to, but not including, position 19 in each log entry. This slice corresponds to the timestamp portion of the log string. By using the same slice object whenever we need the timestamp, we avoid repeatedly writing the index range. This makes the code less error-prone and easier to maintain over time. We begin by printing a short message to signal that we are about to show timestamps using a reusable slice. Then, we loop through each log entry and use this predefined slice to pull out just the timestamp part. By relying on the same slice object instead of repeating numeric positions, we keep the code consistent and reduce the risk of indexing mistakes. The log format has been updated so that each timestamp now includes milliseconds and a time zone abbreviation. To handle this, we create a new list of log entries that use the updated format, where each entry is a string, starting with the timestamp, followed by the user action description. This structure lets us later adjust the slice operation that extracts the timestamp. So all related processing automatically adapts to the new format without changing the rest of the code. We update the slice used to read each log entry so it now captures a longer portion of the line, including milliseconds and the time zone abbreviation. By changing this single slice definition, every part of the code that relies on it automatically adapts to the new log format. This keeps the log handling consistent and reduces the need for manual updates across the codebase. We first print a blank line and a short message to signal that we are now using the updated log format. Then we loop through each modified log entry and extract its timestamp using the new slice definition, which now captures milliseconds and the time zone abbreviation. This shows that by updating the slice object alone, we can handle changes in the log format, while keeping the rest of the loop logic exactly the same. This script shows how reusable slice objects can efficiently extract timestamps from log entries. It first defines a slice that selects just the timestamp part of each log string, then applies it to every entry so the timestamps can be printed without repeatedly writing index values. This reduces the chance of mistakes and makes the code easier to maintain. When the log format changes to include milliseconds and a time zone, the slice is updated once, and all timestamp extractions automatically adapt to the new format, demonstrating the flexibility of using slice objects in Python. Hashing and hashability. Immutable hash basics. In Python, a hash is like a numerical fingerprint that represents an object. It is produced by a built-in function that looks at the object's contents and returns an integer that stays the same for as long as the object exists. This only works reliably for objects that cannot change, such as numbers and strings, which is why immutability and hashability are closely connected. Because immutable objects keep a consistent hash value, Python can efficiently group, compare, and look them up, much like using catalog numbers to quickly find books in a library. In Python, the hash of an immutable object is based on its value rather than its memory location. This means two strings with the same characters will have the same hash, showing they are equal in content. Because their values cannot change, Immutable objects can safely be used as dictionary keys or set elements, with their hash stored alongside them. When you look up a key, Python uses the hash to quickly narrow down where it might be, then checks equality among a few candidates. Since the value never changes, the stored hash stays valid and keeps these data structure operations reliable. In real programs, immutable types are especially useful for things like unique identifiers, such as email addresses, because their values cannot change and their hash values stay constant. This makes them reliable keys in dictionaries and safe elements in sets, so lookups remain efficient and accurate. Immutable tuples also work well for fixed configurations or combined identifiers, since their unchanging nature ensures they behave predictably as dictionary keys in any hash-based collection. Python code immutable hash basics. Show that immutable objects, such as numbers, strings, and tuples, produce stable hash values whenever their contents are equal. Compare the hash values of different numbers, strings, and tuples that hold the same data to confirm they match. Use this behavior to demonstrate that these immutable, consistently hashed values can be safely used as dictionary keys. We begin by giving the same integer value, 42, to two different variables to show that separate variables can store an identical number. We then do the same with the text value hello, assigning it to two different variables so they both contain the same string. These simple assignments set up a foundation for examining how Python treats equality and hashing when working with immutable objects such as numbers and strings. This example compares two numbers and their hash values. Both numbers are set to 42, so the equality check returns true. The program then uses Python's built-in hash function to compute a hash for each number. Because the numbers are equal, their hash values are also the same. This shows that immutable objects like numbers produce consistent hash values when their contents are equal, which is important when they are used as keys in dictionaries. This example compares two string variables that both contain the word hello and shows that they are considered equal. When we compute their hash values using Python's built-in hash function, the results are also the same because the strings have identical contents. This illustrates that immutable objects such as strings produce consistent hash values when their contents match, which is essential for using them reliably as keys in dictionaries. We create two tuples that both contain the numbers 3, 5, and 7 in the same order to show how equality works in Python. Because their contents and order match, the two tuples are considered equal. This equality also means they share the same hash value. As a result, immutable objects like tuples can be used reliably as dictionary keys when their contents are identical. This example compares two tuples that contain the same elements and shows that they are considered equal. It then computes the hash value of each tuple using the hash function. Because the tuples are identical, their hash values are also identical. This illustrates that tuples are immutable and produce consistent hash values when their contents are equal, which is important when using them as keys in a dictionary. We store a customer's email address as a text value, then combine that email with the number 90,210 to form a tuple. This tuple links the customer's email with a zip code and acts as a unique identifier. Because tuples are immutable, this combined value is stable and reliable when used as a key in dictionary operations. We create a customer lookup dictionary where each key is a tuple combining a customer's email and zip code. This tuple is immutable, meaning it cannot be changed, which makes it a safe and stable choice for a dictionary key. The value stored for this key is a string that marks Alice's primary record. By using the same tuple to access the dictionary, we can retrieve and print this record, demonstrating how immutable objects like tuples work effectively as dictionary keys. This script illustrates that hash values are stable for immutable objects in Python. It shows that numbers, strings, and tuples with the same contents are equal and share the same hash value, which confirms their immutability. The script then uses a tuple containing an email and a zip code as a key in a dictionary, and successfully retrieves a stored value with that same tuple. This demonstrates that immutable objects can be reliably used as dictionary keys because their hash values do not change. Mutable objects not hashable. When we say many mutable objects are not hashable, we are protecting the reliability of sets and dictionaries. Mutable objects, like changing lists or profiles, can be modified over time, which would change their hash value. If such objects were used as dictionary keys, their changing hash would make them hard or impossible to find again. To prevent this, languages often make mutable containers unhashable by default, so they cannot be used where a stable hash is required. This design choice helps avoid subtle and silent corruption of these data structures. It may seem inconvenient that mutable structures like lists cannot be used as keys, but this rule actually guides you toward using stable, unchanging identifiers instead. For example, a customer record may change over time, but it is reliably identified by an immutable customer ID used as the key. By allowing only hashable, immutable objects in hash-based collections, the language enforces a clear separation between identity and mutable state. This separation makes programs easier to reason about and reduces the chance of subtle bugs related to changing data. When working with mutable objects that are not hashable, you need to change how you represent relationships and membership. Instead of putting a mutable container directly into a set or using it as a key, use an immutable snapshot of its contents or wrap it in a custom object with a stable identity. For instance, a system might track bookings with an unchanging booking reference, even if details like seats are updated, or a cache might use a frozen version of configuration parameters while the underlying objects remain mutable. This way, the objects used for fast lookups and membership tests stay consistent over the life of the program. Python code. Mutable objects not hashable. In sets and dictionaries, keys must be hashable, which means their value must not change over time. Mutable objects like lists can be modified after they are created, so they cannot be used as keys and will cause an error if you try. In contrast, immutable objects like tuples cannot be changed, so they work correctly as keys in dictionaries and as elements in sets. This requirement ensures that the identifier used to look up a value stays stable, making dictionary and set operations safe and reliable. We begin by creating a list called the route list that holds numbers representing mile markers along a route. This list is mutable, which means we can change, add, or remove mile markers later if needed. After creating it, we display the current contents so we can see the initial set of mile markers stored in the list. When we try to use a list as a key in a dictionary, Python raises a type error because lists are mutable and therefore not allowed as dictionary keys. A try except block can catch this error and handle it gracefully. In this example, when the error occurs, the program prints a message explaining that lists cannot be used as dictionary keys, and then shows the error type, which is type error. This illustrates that mutable objects like lists are not suitable for use as dictionary keys. We convert the list that represents the route into a tuple so that it becomes immutable, meaning it cannot be changed after it is created. This immutability is important because it allows the tuple to be safely used as a key in a dictionary, where keys must remain stable and hashable. After the conversion, we print the tuple to verify its value, confirming that it holds the same data as the original list, but in a form that cannot be modified. A tuple can be safely used as a key in a dictionary because it is immutable and therefore hashable, unlike a list. In this example, the dictionary uses a tuple as the key and stores a value that labels it as delivery truck A. This works without errors and shows that immutable objects like tuples provide stable identifiers. As a result, they are suitable and reliable choices for dictionary keys. When we add a new element, such as the number 50, to an existing list, we see that lists are mutable because their contents can change after they are created. Printing the list again shows its updated state with the new element included. However, the tuple that was created earlier from the original list does not change, which demonstrates that tuples are immutable. This immutability means the tuple can safely serve as a dictionary key, and its identity as a key is not affected by later modifications to the list it was originally based on. This script explains why mutable objects like lists cannot be used as keys in dictionaries or sets, while immutable objects like tuples can. It first shows that trying to use a list as a dictionary key causes a type error because lists can change and are not hashable. The list is then converted into a tuple, which is immutable and therefore valid as a key. Finally, the script demonstrates that changing the original list does not affect the tuple, illustrating why immutable objects provide stable identifiers in dictionaries and sets. Hashing in collections. When we talk about hashing in sets and dictionaries, we are describing how these collections quickly organize and find elements using hash values. Each object is assigned a hash, which points to a specific location where it is stored. To check if an object is present or to retrieve a value for a key, the collection computes the hash and looks only in that location instead of searching everything. This makes membership tests and key lookups fast, even for large collections. The hash function serves as a routing system, sending equal objects to the same place and spreading different objects out to avoid overcrowding. When using sets and dictionaries, you must choose hashable keys whose hash values stay the same while they are stored. Immutable types, like strings and numbers, work well because they do not change, so their hash values remain stable. A dictionary stores both the key and its hash, and during a lookup, it first compares hash values, then uses an equality check to confirm the match. This two-step process makes operations fast and still correct, even when different keys share the same hash value, which is called a collision. Hash-based collections like sets and dictionaries organize their elements by hash buckets, rather than by the order in which you insert them. As a result, the printed order of elements may not match the insertion sequence, and two sets with the same contents can appear in different orders. This internal structure also means performance can suffer if many keys produce similar hash values. Understanding how hashing works is important when building things like customer record indexes or computation caches, because it helps you design efficient data structures and diagnose performance problems. Python code, hashing in collections. Sets use hashing to support very fast membership checks by computing a hash value for each element and using it to decide where that element is stored. This makes checking whether a value is in a set much faster on average than checking membership in a list, which must scan through elements one by one. Conceptually, elements in a set that are considered equal end up in the same bucket, meaning they share the same hash location. Together, these ideas explain why sets are typically preferred over lists when you need frequent membership tests and do not care about order or duplicates. The script starts by importing the time module so it can measure how long operations take to run. This module offers time-related functions, and in this context, it is used to get precise timing information. By using a high-resolution timer from this module, the code can accurately measure execution time and compare the performance of different data structures. We first build a list of evenly spaced integers by generating numbers from 0 up to 1 million in steps of 10. Then we convert this list into a set. The key reason for creating the set is that sets use a hash table structure, which makes checking whether a value is present much faster than with a list. With both the list and the set prepared, we can later compare how quickly each structure supports membership checks. We choose two specific integer keys to test membership checks in different data structures. The first key, 500,000, is an example of a value that is present in the collection. The second key, 500,001, is an example of a value that is not present. By comparing how quickly each structure handles these two cases, we can evaluate their efficiency for checking both existing and non-existing elements. We measure how long list membership checks take by using a high-precision performance timer before and after a block of work. Inside this block, we run a loop 1,000 times. During each loop, we test whether a known key is present in a list of keys and whether a different key is missing from that same list. Repeating these checks many times simulates a typical membership checking workload. When the loop finishes, we read the performance timer again and use the difference between the start and end times to find the total time spent on these list membership operations. We measure how long membership checks take for a set by first recording the current time with a high-resolution performance counter. Then we run a loop 1,000 times, and in each iteration, we test whether a known key is in the set and whether a missing key is in the set. These checks use the set's hashing mechanism, which makes membership testing very fast. After the loop finishes, we record the time again and compute the total duration. This total time lets us compare the performance of set membership checks with those done on a list. Imagine we create one key by writing out a full string, and another key by joining two shorter strings that form the same text. Even though they are built in different ways, they end up with exactly the same string value. In hash-based collections like sets and dictionaries, this means they also share the same hash value. As a result, they behave identically as keys and are placed in the same bucket inside the data structure. We first compare how long it takes to check membership in a list and in a set by measuring the time difference between the start and end of each operation. This shows that sets are more efficient because they use hashing buckets. We then show that two keys which are conceptually equal produce the same hash value, so they behave the same way when stored in a set. Finally, we confirm that these equal keys also act identically as dictionary keys, reinforcing that equal keys share the same bucket in hash-based collections. This script compares how quickly sets and lists can check whether a value is present, showing that sets are much faster because they use hashing. It builds a list and a set with the same integer keys, then measures the time to look up both an existing key and a missing key in each structure. The results highlight the performance advantage of sets for membership tests. The script also shows that two different string variables with the same content produce the same hash and behave identically as dictionary keys, illustrating that equal keys share the same bucket in hash-based collections. Formatting and character codes. Format specifier basics. When you convert values to text in Python, you are choosing how they should appear, and format specifiers give you precise control over that appearance. They let you set things like the number of decimal places, whether to use scientific notation, and how to align or pad the text. This control is especially important for outputs such as financial reports or console displays, where readability is critical. By learning to use format specifiers well, you can make your program's output clear, consistent, and easy to interpret. Formatting in Python lets you control how values are displayed, so your output is clear and audience-friendly. For numbers, you can choose styles like fixed decimals or percentages and set how many digits to show. For text, you can trim or pad strings and control alignment. Together, these options help you present things like data, menus, or logs in a neat, readable way. Format specifiers do more than set width and precision. They also let you style numbers for clarity. You can add thousands separators, choose upper or lower case for hexadecimal values, and force signs to appear for both positive and negative numbers, which is especially important in financial and scientific data. By combining these options, you can tailor how numbers look for different audiences, such as scientists, managers, or end users. This makes format specifiers a powerful way to present numerical information clearly in text. Python code. Format Specifier Basics. This section focuses on using format specifiers to control how numbers and strings are displayed. It shows how to set width, alignment, and decimal precision using formatted F-strings so that output is consistent and easy to read. It also compares the default way values are printed with more controlled formatting, highlighting how proper formatting helps create clear, readable console tables. We define 3 pieces of information to describe a purchase. The price of the item in dollars is set to 12.5. The number of items bought is 3, and the name of the product is notebook. Together, these values can be used to calculate the total cost and to clearly identify the item on a simple receipt or in an inventory list. The code first prints a message explaining that the next outputs will appear without special formatting, setting up a comparison between raw and formatted results. It then displays the price in dollars, the quantity of items, and the item name in their default, unformatted form, so the listener can focus on the underlying data. Finally, it prints an empty line to clearly separate this basic output from any later, more polished versions and to improve readability. We format the price so it always shows 2 decimal places, which is important for displaying currency clearly and consistently. To do this, we use a formatted string that forces the value to appear with exactly 2 digits after the decimal point, a common standard in financial data. After showing the formatted price, we print a blank line to separate this example from others and make the output easier to read. We first print a message to say we are about to show a neatly aligned table. Then, we define a header where the item name is left aligned in a 10-character space, the quantity is right aligned in a 5-character space, and the price is right aligned in a 10-character space. Next, we create a row that follows the same alignment rules, and we also format the price to 2 decimal places. Finally, we print the header and the row so the item information appears in a clear, organized table with columns lined up under their headings. We begin by storing a large integer that represents an annual budget estimate. To separate this example from earlier output, we print a blank line, followed by a short message explaining that we will demonstrate number formatting with a thousands separator. We then format the large number so that it includes commas between thousands and shows no decimal places. This makes the value easier to read and more suitable for displaying as a currency amount. This script shows how formatted strings in Python can control how numbers and text appear in the console. It first prints a price, quantity, and item name with default formatting, then adjusts the price to always show 2 decimal places so it looks like currency. It also builds a simple table where the item name is left aligned and the quantity and price are right aligned to create neat columns. Finally, it formats a large number with commas as thousands separators to make it easier to read. Overall, it demonstrates how formatting improves the clarity and professionalism of printed output. Comparing string representations. When converting values into text, it is important to compare the different string forms a language can produce for the same object. The same value might appear as a readable sentence, a compact machine-friendly token, or a version that exposes hidden characters like tabs or non-breaking spaces. By generating and comparing these representations, you can detect subtle differences and select the most suitable format for tasks such as logging or data exchange. This approach helps you understand that text is a flexible layer built on top of a more complex sequence of characters. When comparing strings, it helps to look at both a readable form and a more explicit form. The readable version shows the text as users normally see it, while the explicit version exposes hidden elements like control characters and escape sequences. Viewing them side by side makes it easier to spot invisible characters, such as extra new lines or tabs, that can change how the text behaves. This is especially important when text moves between systems, like in log messages or data exports, because these hidden differences can break equality checks or cause parsing errors. Understanding how different languages and symbols are encoded is easier when you compare their string representations. Text that looks the same, such as names with accents, mathematical symbols, or emojis, can actually use different underlying code points. By checking both simple and detailed views of text, you can spot and fix encoding differences across platforms, which helps keep customer names accurate and prevents symbol errors in systems like those used for finance. Regularly reviewing encodings in this way helps you anticipate issues, choose suitable data formats, and improve how you process text input. Python code. Comparing string representations. We want to compare different string representations for the same text value by showing a normal, human-readable view alongside a version where special characters are explicitly escaped. Using tools like the representation function and the ASCII function lets us reveal invisible characters such as spaces or new lines and highlight any non-ASCII characters. This helps us clearly see what is actually stored in a string, including characters that would otherwise be hidden or hard to distinguish. We create a text value that includes special characters such as a tab and a new line, written using \t and \n. And we also include a non-ASCII character, the n-, between the price and the word paid. This example is set up so we can examine how different ways of representing text handle these special and non-ASCII characters in the rest of the code. The first line prints a message explaining that the original text will be shown in its normal form, without any special processing. Then the program prints the contents of a text variable that includes special characters such as a tab and a new line. This lets you see exactly how the text appears when printed directly, setting up a comparison with other ways of representing the same string later. The code first prints a blank line and a short message explaining that it will use the representation function to show the string with its escape sequences visible. It then calls this function on the sample text, which returns a version where special characters, such as tabs and new lines, appear as written escape codes. This makes it easier to see the exact contents of the string, including characters that are normally hidden or not directly printable. The code first prints a message explaining that it is using an ASCII conversion function to escape non-ASCII characters. It then applies this function to a text value, producing a version where any characters outside the ASCII range are replaced with visible escape sequences. This makes those characters easy to spot in the output and helps identify or handle text that might not display correctly in some environments. We begin by printing a blank line to separate this section from earlier output. Then demonstrate the format method with special conversion flags. Using the representation flag shows the sample text in its raw stored form, including escape characters such as tabs and new lines. Using the ASCII flag instead converts any non-ASCII characters into their escape sequences, so they appear in a more universally readable way. Comparing these two outputs makes it clear how the same string can be shown either as a raw internal representation or in an ASCII-safe form. This code prints a short message, then loops over 3 special characters: a tab, a new line, and an end dash. For each one, it displays the character in a readable way along with its Unicode code point. The code point is obtained using the ORD function, which returns the integer value that represents the character in Unicode. This demonstrates how Python represents different characters internally as numeric codes. This script shows how different ways of displaying a string can reveal hidden or special characters in text. It first prints a sentence in its normal form, then uses a representation function to make escape sequences like tabs and new lines visible. Another function highlights non-ASCII characters, such as an end dash, by escaping them. The script also formats these different views side by side and loops over selected characters to show their Unicode code points. This helps you understand how characters are encoded and is useful for debugging text that includes special formatting or non-standard symbols. Character code conversions. Character code conversions matter because every visible character in a program is stored internally as a numeric code point. Converting between characters and their numeric forms lets you closely inspect and manipulate text, especially when working with data from networks or files that are encoded as bytes. This understanding reveals how text is stored and transmitted, and it supports tasks like debugging encoding problems, designing communication protocols, and performing security checks based on specific characters. Character code conversions show that the same visible symbol can have different numeric codes, and that different systems may display the same code in different ways. Accented letters, special symbols, and similar characters from different alphabets can each map to unique codes. By converting characters to their numeric values, you can detect these differences and avoid mistakes such as treating distinct characters as identical. This accuracy is especially important for handling international names in databases, normalizing text from web forms, and ensuring cryptographic processes use the exact intended byte sequence. Understanding these conversions helps you design systems that work reliably with complex, multilingual text. Converting characters to their numeric codes is an important way to inspect and clean up text, especially when logging, debugging, or analyzing data. When you see strange symbols or unexpected behavior, these codes can reveal hidden control characters or special spaces that are not obvious on screen. This is particularly useful with text from spreadsheets or web pages, where encoding differences can cause subtle problems. By examining and understanding these numeric codes, you can choose the right normalization steps, fix formatting issues, and keep your program's text output readable and reliable. Python code. Character code conversions. Use character-to-code conversion functions to see the numeric code behind each character and to turn numeric codes back into characters. This helps you notice that characters which look similar on screen can actually have different underlying code points. By revealing these invisible or confusing character codes, you can more easily debug strange text behavior and understand what is really stored in your data. A sample string is created that contains several visually similar characters. A regular capital A, a Scandinavian letter that looks like A with a ring, an accented A, the digit 1, and a full-width version of the digit 1. These characters look alike but have different Unicode code points. This example highlights how text that appears similar on screen can be encoded differently behind the scenes. Understanding this distinction is important for working with text encoding and Unicode. We begin by announcing that we will show each character in a piece of text along with its numeric code. Then we loop through the text, and for every character, we use a function that converts it to its Unicode code point, which is the number that represents that character internally. We print the character together with this number in both decimal and hexadecimal form. This lets us see the underlying numeric codes for the text, which can help when debugging or understanding text encoding problems. We rebuild the original text by converting each character to its Unicode number and then immediately back to a character. These converted characters are joined together to form a new string. We then compare this rebuilt string with the original text to confirm that the conversion process is accurate. Finally, we print messages before and after to indicate that the rebuilding is happening and to report whether the two versions match. This script shows how to convert characters into their Unicode code points using a function that returns the numeric value, and then turn those numbers back into characters with a matching function. It works on a string that includes regular, accented, and full-width characters, and prints each character alongside its code in both decimal and hexadecimal form. This demonstrates that characters that look similar can have different underlying codes. Finally, the script rebuilds the original text from the numeric codes to confirm they match, which is useful for debugging text problems involving invisible or confusing characters. In this lecture, you learn to create and use slice objects explicitly to index and slice sequences in flexible ways. Use hash to inspect hashability and understand how objects behave in sets and as dict keys. And apply format and related built-ins like ASCII and ORD to produce and inspect string representations. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.